In this video, we're going to go over section 3.4 from our textbook, which goes over the chain rule. So first, we're going to introduce composite functions. So for example here, this function m of x is a composite function, and it's a combination of a quadratic function and a cubic function. So to see this more clearly, what we're going to do is break the function up into their composites. So this first one here, y is going to be equal to f of u, where f of u is our function u cubed. So this is our cubic function here. And then u is going to be equal to g of x, which is equal to x squared plus 4. And so what's happening here is that this function here, this x squared plus 4, is getting plugged in to our f of u wherever we see a u. And when we do that, we get our original function, x squared plus 4 cubed. So here's our formal definition of composite functions. So a function m is a composite of functions f and g if it is of this form. So the domain of f is going to be the set of all numbers x, such that x is in the domain of g, and g of x is going to be in the domain of f. So let's look at this example here. We're given that f of u is equal to 2u, and g of x is going to be e to the x. What we want to do is find the composite f of g of x and the composite g of f of u. So I'm going to color code these guys. So f of g of x, we can find this by plugging in our function g of x into f of u wherever we see a u. So this is going to be equal to 2u, and then wherever we see a u, we're going to plug in e to the x there. So this just becomes 2 e to the x. All right, then for g of f of u, what we're doing is we're going to plug in f of u into our function g of x wherever we see an x. All right, so our g of x is e to the x, so we have e here, and then we're plugging in 2u wherever we see an x, so we get e to the 2u. All right. Another way to say this is that our function f is being evaluated at g of x, and then our function g is being evaluated at f of u. All right. It'll also be helpful to look at composite functions and be able to write each function as a composite of two simpler functions. So we'll do that with this example here. We have y is equal to 50e to the negative 2x. So we have our outside function, or our parent function, as e to the x. That's the parent function that we have here. And so y is going to be equal to 50e to the u. Because our parent function is e to the x, and this is a function of x. So u is going to be a function of x that's going to be plugged into this guy here. So we'll get u is going to be equal to negative 2x. All right, so this is our inside function that gets plugged into our parent or our outside function. Same thing with b here. We have this composite function, and if you recognize our parent or our outside function is going to be the third root. We have a third root function. So our outside function is going to be this here. And then u, whatever u is going to be plugged into our outside function. That's going to be 1 plus x cubed. And then just checking our work, if we were to plug u into there, we would get our original function. All right, so that's how we would break up a composite function into two simpler functions. Now this brings us to the general power rule. So if we have a function u of x here, and it's differentiable, and n is any real number, and we have a function of this form, then the derivative of this guy is this here. And so this is an example of a composite function. And the book goes over a few examples using the product rule and to find a pattern that demonstrates this general power rule. So if you'd like, you can go check out how they did that. And then here's some simplified notation as well using y prime d dx and so on. So let's look at these examples here. For A, we want to find h prime of x if h of x is equal to this here. So this is a composite function. And so our outside function, I will just call h, is x cubed. And then our inside function, or sorry, we'll write this as u cubed. And then our inside function u is 5x plus 2. So this guy's getting plugged into this u here to get our equation. So following the general power rule, h prime of x is going to be essentially the derivative of our outside function evaluated at our inside function. So we're just going to look at the power of our outside function. So this 3 is going to come down in front, and then our inside function is going to be to the power of our 3 minus 1. And then this is being multiplied by the derivative of our inside function. All right, so then we get and then we can just write this as 15 times 5x plus 2 squared. All right, now let's look at B. Similarly, in this case, our y, our outside function, is going to be u to the 5th power. And then our inside function, u, is going to be equal to what's being plugged into our u here. And that's going to be x to the 4th minus 5. All right, now following the same general power rule, remember we're going to look at the power of this guy. 5 is going to come down in front, and then this inside function is going to be to the power of 5 minus 1. Just following this here. So we get 5 times x to the 4th minus 5 to the power 4. And then we're multiplying that by the derivative of our inside function. So that's going to be, actually, I'll just to stay consistent, write the notation. All right, so then taking the derivative of our inside function, we're going to get 4x cubed. Just doing power rule on this guy, and then we know that the derivative of a constant is 0. Right? And so then we'll get 20x cubed times x to the 4th minus 5 to the 4th. All right, so this brings us to the chain rule. So we've used this general power rule that we saw in these examples to find derivatives of composite functions of the form this here, where our function f of u is a power function. But we want to see what happens if f is not a power function. When doing so, we find a more general rule, the chain rule, and it allows us to compute the derivatives of many composite functions of this form, so functions that are not just power functions. And so doing the 4-step process and taking the limit of our difference quotient, we're able to show this here. So if we have a composite function here, f of g of x, where y is equal to f of u and u is equal to g of x, we know that the derivative is going to be the derivative of our outside function evaluated at our inside function times the derivative of our inside function. So essentially the derivative of the composite of two functions is going to be the derivative of the exterior function evaluated at the interior function times the derivative of the interior function. And so that is the notation that's used in this theorem here. This capital E is going to stand for exterior and the capital I is going to stand for interior. So if we're given a composite function where we have this exterior function evaluated at this interior one, the derivative of that guy is going to be the derivative of our exterior function evaluated at the interior times the derivative of our interior function. All right, and of course, provided that these derivatives do in fact exist. All right, and then we can also write this in this way. So let's look at a few examples here. Let's look at A. So the first thing I'm going to notice for A, again, is to break up our interior and exterior functions. So we immediately see that this 2x cubed plus 4 is going to be our interior function, and our exterior function is going to be x to the power negative 5. And then interior will be 2x cubed plus 4. All right, and we know that that is true because if we were to plug in our interior function into this x value here, we get our original function. All right, so finding the derivative of this guy, we'll use the chain rule. So we're going to find the derivative of our exterior function evaluated at the interior and then multiply that by our interior function. So exterior, we bring the negative 5 down in front, still evaluated at our interior function, and then we get to the power negative 6 because we're taking the derivative of this guy, and so we know that it'll be negative 5 minus 1 to the power of that. Right, then we're going to do the derivative of our interior function. So we get, this guy stays here, and then the derivative of this guy, we're going to get 6x squared, and then the derivative of 4 is just going to be 0. And then multiplying this out, so multiplying negative 5 and 6x squared, we get this here. All right, so not too bad. Looking at B, going to do the same thing. Let's identify our interior and exterior functions. So we're familiar with our outside function, our parent function e to the x. And then we're just going to be plugging in our interior function into that value here. And just checking this, just so that doesn't look like it's in the exponent. So just checking this, if we were to plug in our interior function into this x value here, we get our original function. So now let's find the derivative of that guy. So we'll look at the derivative of our outside function, e to the x, or in this case, e to the x, but evaluated at 3x to the 4th plus 6. But remember, the derivative of our exponential function is just our exponential function. So we just get this, and then times the derivative of our inside function, which was 3x to the 4th plus 6. All right. So the derivative of that, we'll get 12x cubed, and then the derivative of 6 is just 0. And then we can write this as all right, so that's the derivative of this guy. And then lastly, we have part C here. We'll identify our exterior function, which if you look here, we have ln. So our exterior function is going to be ln x, and then our interior function that we plug into x will be x squared plus 9x plus 4. All right, so using the chain rule, we're going to take the derivative of our outside function, our ln x, but evaluate it at the interior function. And if you remember, the derivative of ln x is just 1 over x. So if we're taking the derivative of that evaluated at our interior function, instead of 1 over x, it'll be 1 over this guy. And then we're going to take the derivative of our inside function. So we'll get this guy stays here. And the derivative of that guy is going to be 2x plus 9. And so this is our derivative. All right. So the chain rule can also be extended to compositions of 3 or more functions. So for example, if we had y, w, and u, these functions here, then the derivative dy dx is followed by this guy here. And so we'll do an example of this. So let's identify our functions here. Y is always going to be our exterior function. And in this case, it will be, and just following, I'm just going to keep following with these variables. So if y is a function of w, I'm going to write this as w cubed here. And then w is what we're going to be plugging in for this guy. And it's going to be a function of u. And we have ln of this guy here. So that's going to be ln of u. And then u is what's plugged into our function w, and it is a function of x. And that becomes 1 plus e to the x. All right, so this is a composition of 3 functions, and these are the 3 functions. And so we're just going to use this formula here to find dy dx. All right, so the first thing we'll look at is the derivative of y with respect to w. So then we get 3w squared there. Then we're multiplying the derivative of w with respect to u. So that'll just be 1 over u here. And then we're looking at the derivative of u with respect to x. And so we just get e to the x there. All right, but we need to plug in the values that we have for w and u here. So we get 3w squared, and we know that w is going to be ln of u. And then we're going to multiply this by 1 over u times e to the x. But we also want to plug in our values for u here. So let's actually just do that. All right, so just plugging in what we got for w and u into dy dx here. And then just doing a little bit of simplification here, we'll have 3 times e to the x, so just multiplying these guys. And that's multiplying ln of 1 plus e to the x. And this will be all over 1 plus e to the x. All right, so that'll be it for this video.